Hello, my name is Eric Segan. Welcome to the webinar, Introduction to FPGA Design Using MATLAB and Simulink. Presenting with me today will be Jordan Enkelis. Jordan is Altera's Senior Product Manager for Software and DSP products. Many engineers have adopted MATLAB and Simulink to develop DSP and related algorithms. With FPGAs increasingly being used for algorithm implementation, the challenge for design teams is to get these algorithms into FPGAs more quickly with efficient implementations. Because of developments at both MathWorks and Altera over the last decade, FPGA design using MATLAB and Simulink is now readily available using mature, robust workflows. Today we will demonstrate two such workflows. Let's start by looking at the FPGA design process to see what problems occur with the algorithmic designs and highlight how workflows based on MATLAB and Simulink can help. What's common to algorithm implementation in FPGAs is that there are usually two main contributors to a design project, the system designer and the FPGA designer. The system designer and FPGA designer often have different views on algorithm implementation that complicate the design process. Let's look at this further before we get into the demo. The system designer is centered on the development of the algorithm, usually starting off with a floating point algorithm and then converting it into fixed point form. The designer will be concerned with timing, with integration of control logic. They tend to be concerned with evaluating different architectures, different possibilities, different types of FIR filters, for instance. They also need to integrate in existing algorithmic IP with any new content they're producing. In addition to creating the design itself, they need to be concerned with the overall system test bench, the overall environment that's being evaluated, any adjacent analog or digital models, as well as existing algorithmic IP that could be acting as part of the test bench. They will often iterate on this exhaustively and combine it with overall FPGA requirements. This all tends to get handed off to the FPGA designer, who's starting off often with an RTL design flow, is concerned with integrating the new algorithm with other IP, with memories, with other I/O, and so on. They are generally doing that RTL development, then running behavioral simulation to start off their functional verification process. They'll go ahead, do synthesis to get some initial assessment of the resources that will be required to implement the design. Then they can proceed with the remainder of the implementation of the process, get more detailed timing information on the design, and iterate here to improve the resulting implementation to get higher frequency to drive down the resource utilization. Okay, so this is generally the two different views here. The difficulty is you have multiple representations of the design floating around here. It means that you've got to have multiple levels of verification as well. It can be difficult to respond to changes in specifications because now those changes have to be propagated down through the design process. So bottom line is there's issues with design and issues with verification. So what we're talking about here today is more of a model-based design approach where instead of having different representations of the design, you're beginning with algorithms in MATLAB and Simulink. From those, you can generate your RTL directly using automatic code generation capability. And then you have the ability to verify that generated HDL using MATLAB and Simulink designs as your system test bench. You also have the ability to drive the downstream FPGA tools, such as Altera's Quartus 2, and to run verification using HDL simulation. You have the ability to back annotate the timing information into the original Simulink model, and you have the ability to drive down into FPGA development board hardware. So again, you're working off of a common design description, and you're driving the entire design process, giving you greater ability for iterative design improvement. So we're going to be talking about two products today. For MathWorks, the Simulink HDL Coder product, and from Altera, the DSP Builder product and its advanced block set. These tools are based on Simulink workflow. So first, let's look at Simulink HDL Coder get into a demo, and then I'll hand off to Jordan. He can give us more insight on Altera DSP Builder. Simulink HDL Coder supports HDL code generation from MATLAB code, Simulink models, and stateflow charts. The HDL code that it's generating is target independent. So you can go to different types of FPGAs, you can go to ASICs, all off of that common HDL code. It's either in VHDL form or Verilog, of course. And then for verification, we support the ability to do verification using a standalone HDL test bench in your HDL simulator of choice. MathWorks also offers co-simulation interfaces between MATLAB and Simulink and either MetaGraphics ModelSim or Cadence Incisive. So these give you the ability to use a system-level test bench in MATLAB and Simulink and verify with the HDL simulator you're using. The other aspect of HDL Coder is its workflow integration. It helps you drive down into Cordis 2, as we'll see a little bit later. That helps you do further optimization. You can go to the point of driving a bit stream into a development board, and you have the ability to extract information out of the placed and routed design so you can annotate timing back into the Simulink model. To demonstrate Simulink HDL Coder today, we will use a digital down converter, or DDC, design. This DDC takes a high rate signal, about 70 megasamples per second, and goes through several digital filter stages to bring the signal down to a baseband rate of about 270 kilosamples per second. As we perform this model-based design process using Simulink HDL Coder, we will pass through several distinct phases. We will start with a floating point model that acts as a reference model and an executable specification that captures the system requirements in the model itself. From there, we'll go to a fixed point model, and we will be verifying that the performance of that fixed point algorithm compares well with the original floating point reference. From there, we'll go on to an implementation model for hardware. Using that model, we can verify whether the architectural and implementation trade-offs we're making are helping us to meet the system requirements and specifications. And we can look at tuning the design further using optimizations in HDL Coder, such as getting more serial implementations of filters, introducing pipelining, and so forth. From that implementation model, we can generate the HDL code, and we can verify it against these higher level representations. As we go through this, we certainly won't have enough time to do this every single step, but we'll highlight on some of the things you can encounter in each one of these levels. So let's proceed into the demo. To start with, if you're not used to Simulink, we've started out here with the library browser so we can see the different libraries that are available to us. If we want, we can just start creating a model from scratch here, taking some of the building blocks here, dragging and dropping them into this new model here, connecting them up as we see fit and so on. We can build up a model from scratch in this fashion. But let's go ahead and start with the DDC. So what we're looking at here is the floating point version of that, which serves as our executable specification. Going from left to right, you see the input stimulus. That's going to be a chirp signal. We see the design itself that we're ultimately going to take to fixed point and to HDL and beyond that. And then we have a scope that we're going to use to look at the spectral response from the DDC. If we look within the DDC itself, we see the structure we showed in the PowerPoint, and we can go ahead and descend into the hierarchy and see the multi-stage digital filter. You see the different colors on the Simulink model. Those represent the different sampling rates in the design. So we'll go ahead and start a simulation running. And in red here we see the specified threshold for the DDC, and the blue signal is the evolution of the spectrum response as we feed in this chirp signal. So this is our intended behavior for the design. So now let's bring up a diagram here that has on top the floating point reference that we just showed, and below a fixed point version of this, an attempt to bring this into a fixed point form. If we look at that fixed point model, same structure, but here now you see that instead of floating point numbers, we have fixed point numbers with different word lengths and different amount of precision. So let's go ahead and simulate that and see how we're doing in this process of going from floating point to fixed point. And as we see here, the blue line representing floating point and the red line representing fixed point are very, very different. So there's clearly a problem with what we've done here in going to fixed point. We've lost fidelity in a dramatic way. So now what we're going to do in order to diagnose this is bring up the fixed point tool. And what we'll do here is, first of all, we need to instrument the design by logging the mins, maximums, and overflows. So we'll go ahead and rerun the simulation. And we're seeing the same response here, just that now we're capturing all that data. We'll let that run a few seconds. And then we'll go ahead and stop the simulation. And what we see here is displayed in this table is the different output signals here, and the one shown in red here is the source of the problem, because what the simulation has reported is we've produced over 22,000 overflows just in that time we were simulating here. So that's where we need to narrow in our focus. So now we need to figure out what's the actual dynamic range that we do need. So what we'll do here is we'll still keep logging data, but we'll override the fixed point settings we put into the model and put in doubles. So we'll go ahead and do that. And now we will rerun the simulation. So now we should get good agreement because we've gotten rid of the fixed point settings. We're getting good agreement between the two models. And let's accumulate data to get a better fix on the necessary dynamic range. Okay. Now we'll go ahead and stop. And we'll ask the tool to propose new fractional lengths, new word lengths that will accomplish the task. So as we scroll through this table, what we'll see is the specified precision and the precision that the tool is proposing. And what we'll see here is these checkboxes indicate where there's a change. The product output, the tool is now proposing that we use go from a 55-bit word length to 48. But we also make some other changes through the data path. So what we can do now is accept those proposed fraction lengths. And then we'll see how that affects the simulation. In order to do that, we need to go back to the local settings at fixed point. So let's go ahead and rerun the simulation now. And now we're seeing much closer agreement, still some departure we'd expect, but you see that it's many dB below the region that we care about. So they're not really relevant to the response of the design. So that's just a bit of a highlight of what you can do within fixed point. So now we've completed the fixed point part of this design process, and we're ready to move on to hardware implementation. So let's close out this model, and now we'll use another model that we have been working on. And in this case, we see the refined fixed point DDC on top, and below we see the HDL implementation form of the DDC. Now, I could have generated HDL directly from the fixed point NCO, but knowing that this is going to be targeted to an FPGA, I can make a change here in the NCO, and that is to use a lookup table. That way it could be mapped to ROM in my FPGA, which will give me ultimately better resource utilization. So we'll go ahead back up to the top level here and rerun the simulation and compare the results of the two forms of the DDC. We can see that there are some differences as you get out here, but at that point you're 60, 80 dB below the threshold. They're not really relevant, and that represents a reasonable trade-off to make it a system level in the implementation of the DDC. So Now we're ready to proceed on to HDL code generation. And the way we can do that is to launch the HDL Workflow Advisor. And what the HDL Workflow Advisor does is it organizes and sequences all the tasks involved in HDL code generation. So you can see it includes, at the top level, setting the target device, doing some work to prepare the model for code generation, the code generation itself, and then the downstream implementation flow with Quartus 2. So we'll start off by setting the target. We'll go ahead and switch this over to a Simulink4 GX part. We'll choose one of the larger ones there, and then we'll go ahead and run this task. So we can run these task by task, or we can go ahead and say run through a given task. So now what we're doing is checking the overall settings to make sure they're ready for HDL code generation, making sure all the blocks in the model are compatible with code generation, and getting generally prepared for that code generation process. Okay, so now we're all set, and let's look at the code generation options here. So we've got some basic options, including the language you're going to generate, VHDL or Verilog, what sort of reports you want to generate out of this process, so we can get the visibility on the way you've generated the code. We have a fair number of options over the form of the HDL, naming of the files, clock signals, and so forth, as well as test bench options as well. So we'll go ahead and do that and start that process and the RTL code generation itself. So we'll get that started and let that run. Okay, so now we're done with the code generation process. What we're looking at here is a report that was produced by the tool, and this is the summary report. We can look at more detailed reports, such as getting a view of the resource utilization throughout the design, or we can view the generated HDL. So let's go ahead and do that. So here we're looking at an example of the generated code. You can see it's pretty well structured. You can see that the naming of the signals corresponds to the blocks within the original Simulink model. And then you see these links embedded throughout the generated code. So by clicking on these, we can browse back to the model corresponding to the block of the model that corresponds to that generated HDL code. So that gives us some traceability going back. At this level, we could go into any given part of the model. If we wanted to go back and iterate now, we could go into a block like in this filter. If we want to change coefficients, we could do that and regenerate the code in the way that we just produced it. We also have control over some of the HDL settings here. For instance, for this block, you see a number of parameters here related to pipelining and serialization of that block. So what you have are a lot of options for controlling whether you want to do resource sharing, whether you want to insert additional pipeline stages, and so forth. These are kind of worthy of a whole webinar in their own right. So I'd like to point you to another webinar we have done recently called Accelerate FPGA Design using Simulink HDL Coder. And in the parting slide of today's webinar, I'll give you directions on how to reach that. But I think that's a very good resource. It gives you a lot of detail on how to do that. You can also browse from the model back to the generated HDL code. So let's go and do that. And here you see that we've browsed to the corresponding code to that filter stage. So that wraps up what we want to cover today in the demonstration. So let's recap what we saw in the Simulink HDL Coder demo of FPGA design using MATLAB and Simulink. We saw how we could start with a floating point model in Simulink and how we could compare it with a fixed point model as we prepared for hardware implementation. We showed how the use of data logging with a fixed point tool could be used to diagnose issues with the fidelity of the fixed point model. Then we saw how the fixed point tool assisted us by proposing changes in word length and precision, resulting in a fixed point model that captured the required fidelity without making the design larger than necessary. We discussed how we then worked with a hardware implementation model that included design refinements intended to improve the FPGA implementation in Altera devices. We showed how the HDL Workflow Advisor steps us through the HDL code generation process, from choosing a target FPGA device, through preparing the model for code generation, and ultimately for targeting the design to the Altera Quartus 2 implementation tools. We also saw that Simulink HDL Coder produces very readable HDL code that can be traced back to the Simulink model from which it was generated. And finally, we showed how further refinements and optimizations could be made in an iterative design process. Simulink HDL Coder now supports over 170 blocks from the core Simulink block set, as well as the DSP system toolbox and the communication system toolbox. That means that you can reuse many of the algorithmic models you may already have and shorten the process of preparing models for HDL code generation. This slide highlights many of the supported Simulink blocks from these different block sets. One of the more powerful blocks supported by Simulink HDL Coder is the MATLAB function block. Using the subset of the MATLAB language appropriate for hardware implementation, you can describe many types of systems in a textual format. Along with the MATLAB function block, we provide a set of MATLAB function block design patterns for HDL. They act as a set of worked examples that you can use or treat as templates that you can adapt to your design. The MATLAB function block design patterns include counters, shift registers, muxes, demuxes, finite state machines, line buffer RAMs, conversion between real, imaginary, and complex numbers, and even bit twiddling examples. Another popular way to build state machines for use with Simulink HDL Coder is through Stateflow, a graphical tool for finite state modeling that's tightly integrated with Simulink. So between the MATLAB function block and Stateflow, you can choose between text-based state machine modeling and graphical state machine modeling. So I'd like to highlight some of the use cases where we think that Simulink HDL Coder is a very good fit for FPGA design. First of all, for system-level designers who are relatively new to hardware design, we think that you'll find it easy to use HDL Coder because, first of all, you can use existing algorithms you've produced in Simulink using the core Simulink block set as well as the DSP and communication system toolboxes. So that means you don't have to map the design to a different block set in order to do HDL code generation. Also, the HDL Workflow Advisor, because of the way it sequences the HDL code generation process and integrates with tools like Quartus 2, makes it relatively easy to work into a hardware design workflow. For companies who are already today using model-based design in a significant way, especially those who are using model-based design for embedded software code generation, you will often find that it's relatively easy to adopt Simulink HDL Coder into your workflow. In cases where target-independent HDL is needed to support various types of programmable logic devices, as well as ASICs, Simulink HDL Coder's ability to produce target-independent HDL is quite valuable. For those who are involved in safety-critical applications where DO254 workflow support is needed, Simulink HDL Coder has many good capabilities that support that approach. In cases where an algorithm may be targeted either into software or to hardware, the fact that there's C code and HDL code generation from Simulink makes it a good tool for those types of situations. And finally, in cases where the algorithmic model includes MATLAB code or stateflow charts, then Simulink HDL Coder is a very good solution for that. So at this point, I'd like to turn over the presentation to Jordan Inglis, and he'll talk to us about Altera DSP Builder.
Thanks, Eric, and thanks to the MathWorks for the opportunity to co-present today. In the beginning of the presentation, you saw how powerful the MATLAB Simulink, or model-based design, can be in improving FPGA design productivity. Eric also highlighted the MathWorks Simulink HDL coder. In the next section, I will cover Altera's DSP Builder tool. DSP Builder is a plugin to the Simulink environment and generates HDL optimized for Altera's FPGAs from Simulink. Once purchased, you will see both the standard and advanced block set. DSP Builder has many key optimizations, such as being silicon aware. DSP Builder ties back to Quartus 2 software for all timing-based information on the device you select within DSP Builder. In addition, there is automatic pipelining to meet the specified Fmax and make latency trade-offs. Finally, DSP Builder provides optimal portability, easily allow you to upgrade your silicon to future Altera FPGA families. A major new advance with DSP Builder in the last 6 months has been the addition of the floating point capability. Using the floating point compiler within the DSP Builder tool, significant optimizations are made automatically to reduce logic and routing, which provides high-performance floating point capability in an FPGA design. Let's look about how to get started with DSP Builder further. Simulink consists of a number of libraries of building blocks from which designs can be built and tested. DSP Builder is shipped with 2 library add-ons to the MATLAB Simulink tools, encapsulating 2 preferences for design methodology: a WYSIWYG style, giving explicit control over pipelining and reset and enable signals in the standard block set, and an abstracted, higher-level style in the advanced block set, which allows the tool freedom for automatic optimization and pipelining. Both block sets generate HDL, provide automatic verification that an RTL simulation of the HDL generated matches the Simulink simulation, and generate Quartus projects and QSYS integration files. The classic block set also provides tools for Simulink-driven hardware simulation and signal capture from the SignalTap2 logic analyzer. The first screen you can see is constraint-driven design, where we can choose the data type. As of 6 months ago, DSP Builder supports both fixed and floating point types. Second, you would create a model. These designs can be created using IP blocks for common functions like filters, NCOs, saturate, and truncate blocks. Or the engineer can build their designs out of primitive blocks, such as multipliers, adders, muxers, delay blocks, and so forth. Or any combination. In any case, all design optimizations are applied across the whole design. Next, we would select the device. Changing FPGA device families is simple as selecting the family and speed grade, or even a specific device. The DSP Builder tool has access to the timing models of each device in Quartus 2 software, which allows the tool to perform device-specific optimizations. This facilitates design migration to newer Altera devices. Next, the designer specifies the desired clock frequency. The tool is capable of building designs with performance on par with the best hand-optimized HDL implementations. In this case, the tool closes timing with a worst-case clock rate of 408 MHz, as confirmed by the Quartus 2 software compiler. Math.h functions are the simple operations you'd expect in the simple C library math.h. Trigonometric, log, exponent, inverse square root, etc., as well as the basic operators such as divide. The implementation is multiplier-based, since Altera FPGAs have an abundance of high-precision multipliers. Traditionally, Cordic implementations have been used for such operations, but the logic for this choice is based on the outdated ASIC idea that logic is very cheap and multipliers relatively expensive. For floating point operations on an FPGA, multiplications are now cheap and have the advantages of predictable performance, low power, and low latency. Contrary to accepted wisdom, the multi-stage Cordic approach is a highly inefficient method to build these functions. The comprehensive library support within DSP Builder Advanced Blockset allows customers to build large, complex, and highly optimized floating point data paths. Fuse Data Path has been integrated into Altera's DSP Builder Advanced Blockset toolflow. Complex equations can be easily implemented in DSP Builder Blockset within MathWorks Simulink environment. This allows for easy fixed and floating point simulation, as well as FPGA implementation of engineered designs. DSP Builder supports complex numbers in fixed point or single or double precision. The variable types are inherited unless overwritten by the engineer. If we look under the subsystem doing the simple math, we note how floating point complex types, both single and double, are used in conjunction with fixed point types. The tool then offers a single environment for building mixed floating and fixed point designs, and offers abstraction of complex and vectors, making design simple and productive. All the issues of dealing with mantissa, exponents, normalizations, and special conditions are abstracted away, just as when using floating point in the software flow. For a while, looping blocks are provided to allow for control functions within DSP Builder. These loop blocks can be nested to provide more complex looping behavior, similar to what you have in software constructs. This provides a summary of the DSP Builder getting started flow. Just before handing off to me, Eric highlighted the benefits of Simulink HDL Coder, including targeting system-level designers, targeting independent HDL, and safety-critical applications. DSP Builder adds additional benefits when using this. Several of them include hardware designers new to model-based design, generation of HDL that is optimized for Altera devices, even ones that we haven't even built yet, the ability for constraint-driven designs for high performance, the ability to support floating point implementation, and support of integration into larger systems with QSYS. That concludes my section. I'd like to hand it now back to Eric.
Thank you very much, Jordan. So now let's discuss some next steps that you can take in order to learn more about Simulink HDL Coder and Altera DSP Builder. First of all, you can visit mathworks.com/FPGA. There you'll find access to a wide variety of links to technical papers, to webinars, to videos, and other sources of information on how Simulink HDL Coder supports FPGA design and how it works with Altera's workflow. In particular, you'll find the ability to request an FPGA design information kit. There you will get access to a large number of webinars and technical papers, including the webinar Accelerate FPGA Design Using Simulink HDL Coder. That's the one I mentioned earlier that goes into a lot of detail on how you can use the optimizations in Simulink HDL Coder to improve your quality of results. Also, you can request a trial license for Simulink HDL Coder so you can get direct hands-on experience with that tool and see how it works in your workflow. Another source of information you can go to is altera.com/DSP Builder. There you'll find white papers, application notes, and trial request forms so you can get access to that tool and more detail about its use. The third thing we can offer is that you can send email to alteraexpert@mathworks.com. That email is monitored by our application engineers who can respond to your specific questions on the use of these tools we've covered here today. So that concludes the webinar here. So you should be submitting your questions via the WebEx session here. Give us a minute to scan through those, and we'll start responding to your questions.